Lab 21, Example 1. We want to determine some key information for the following quadratic function. We have f of x is equal to 2x squared minus 16x plus 47. The first thing we want to do is find the vertex. The first way I'm going to show to find the vertex is using this while it's in standard form. What I mean by that is it is in the form of ax squared plus bx plus c, where a, b, and c are real numbers. The alternative to standard form is shifted or vertex form, which is f of x is equal to a times x minus h squared plus k, where the vertex is hk. So the first way I'm going to show is just finding the vertex using it when the function is in this form. So if we want to find it while the function is in this form, we have to find a point. And like any other point, we have a point where there's an x value and where there's a y value. So first what we're going to do is we're going to find the x value. And the x value is given by the formula x equals negative b divided by 2a. So plugging straight in, we have b is negative 16. So you have negative 16 divided by 2 times a, which is 2. So a negative of negative is a positive, and 2 times 2 is 4. 16 divided by 4 is 4. So we have our x value, which is 4. Now that we have our x value, we need to find our y value, and we can do that taking our x value as 4 and plugging it into this function up here. So we have f of 4 is equal to 2, 4 squared minus 16 times 4 plus 47. And if you plug this into a calculator, you find that this is equal to 15. So our point, our vertex, is the point 4, 15. So that's the first way of finding a vertex using the function when it's in standard form. The other way is to put this into shifted / vertex form, and then you can immediately tell what the vertex is. So shifted form is the form when you have f of x is equal to a times x minus h squared plus k. So you have a perfect square in there. And your vertex is simply given by hk. So if you have your function in this way, you already know what your vertex is. So we're going to move our function, we're going to manipulate it to get it into this format. So this is the second way to find our vertex. So we have f of x is equal to 2x squared minus 16x plus 47. So I'm just going to write that here. What we need to do is we need to find a perfect square. We need to get a perfect square in here somehow. So what I'm going to do is I'm going to group off our x's here. And the first thing I'm going to do is find this number here 2, see if I can factor it out. And it turns out I can, because 2 goes into 16, so I can factor 2 out of 16. So we can rewrite this as 2 times x squared minus 8x. And I'm going to put a plus little place here, placeholder, just for a placeholder for the moment, plus 47. So the next step after you factor that out and you get this little bit right here is we want to add a number into here. And whatever number we add into this place will make this polynomial into a perfect square. So the way we know what to add here is we're going to take our b here, we're going to divide it by 2, and then we're going to square it. This is just always how you perfect a square when you have it like this. So you have negative 8, which is our b, you divide it by 2, and then you square it. And you'll find that negative 8 divided by 2 is negative 4, and then negative 4 squared is 16. So the number that goes here is going to be 16. Now we can't simply add numbers willy-nilly. We need to have our equation be balanced. So normally we would subtract 16 over here to keep it equal, but remember that we are actually multiplying whatever is in these parentheses by 2. We took out the 2, but we still have to multiply it in. So actually what we added was not 16, we added 2 times 16. So we need to subtract to make sure that this is the same function. We need to subtract 2 times 16 so that we don't come up with an entirely different function, so that our function remains the same. So now that we have that, we can rewrite this function as 2. This is going to be a perfect square. We've made it so. If you factor this, you find that it is x minus 4 squared. And if you add these, you find that it is plus 15. And this is in shifted form. You see our a is 2, and our x minus h is x minus 4, and it's a perfect square, and our k is 15, which means that our vertex is given by hk. So if we look here, we have h is 4, and our k is 15. So we know, simply by having it in this form, that our vertex is the point 4, 15. And you notice that it's the same as what we got over here from when we did it the other way. So that is 2 ways to find a vertex of a quadratic function. Moving on, we need to find some other information. So the next thing we need to find is, does the parabola open up or down? So we can figure out if a parabola opens up or down. If we look at our shifted vertex form here, this number a, which is 2, if it is positive, then it opens up, and if it's negative, then it opens down. So we have a is equal to 2, and if a is positive, so if it's greater than 0, that's another way of saying positive, then it opens up. And if a is less than 0, so if it's negative, then it opens down. So we have a is equal to 2. 2 is greater than 0. It's a positive number. So we know that our parabola opens up. The next thing we want to do is we want to find the domain. The domain is any value, it's what our x values can be. And for any quadratic function, any at all, it's always going to be all real numbers, or that is negative infinity to infinity. Because for every x that you put into the function, you will find a y. That's another way of saying that. For our range, I'm going to draw a little handy dandy graph here, just a little quick sketch. We have our vertex at 4, 15. I'm just going to put here, it's not quite to size, but let's pretend here's 4 and here's 15. We know that it opens up. I can't draw apparently. So our range is going to be whatever possible y values we have. So if we have a y value down here and we go out looking for our function, we don't find it. We can't touch the function down here. Same thing for up here, same thing for up here. But as soon as we get to 15, we go across and oh, we touched our function. And the same thing happens for when we go above 15. So we go, oh, we touched our function, oh, we touched our function. So our range, going from bottom to top, like we always do, is it starts at 15 and includes 15, and it goes up into infinity. If you go above 15, you will always be able to touch the function if you go horizontally. And with this graph, we can also demonstrate why the domain is negative infinity to infinity, because if you did vertical lines for every x value, no matter how far out you go to the left or to the right, you will always have a value to touch your function. So that's another reason why our domain is real numbers and our range is 15, including 15, to positive infinity. So now that we've figured out that, we're going to have a little aside. If we wanted to graph y is equal to f of x, how should we shift the graph of 2x squared? So this is asking if we have a parent graph, y equals 2x squared, what should we do to this graph? How should we move it to get our function, which our function, I'll leave it as the child graph. Our child graph, which is what we have, is 2x squared minus 16x plus 47. Now, this is in standard form. I'm actually going to show transformations in the vertex shifted form. So I'm going to rewrite this as y is equal to 2 times x minus 4 squared plus 15. If we have it in the vertex or shifted form, it's way easier to actually see any kind of translations or shifts that we have moved in a graph. So if we compare this graph to this graph, or this function to that function, we see that instead of writing x, we've written x minus 4. And if we have a minus 4 with our x, and we're in that area with our x value, anything with our x means we're going to move either left or right on our graph. And if we minus something from our x, that actually means we're moving to the right. So because of this x minus 4, we're actually shifting our graph to the right 4 spaces. The next thing we notice from this to this is we have 2, this right here is standing for the x squared, and then we added 15. So we added 15 to our parent graph. If we add a number, that's going to be a vertical shift up. If we subtract a number, that's going to be a vertical shift down. So because we added 15, like separately to our function up here, this is a vertical shift up 15. So essentially moved our parent graph, which was y equals 2x squared, to the right 4 spaces and up 15 spaces. So that's just a little aside. Moving on. Next we're going to ask, where is f of x increasing / decreasing? So our vertex, this is for reference's purpose, our vertex was the point 4, 15. And I'm going to redraw our little graph here. We have 4, we have 15, we know it opens upwards. So this question is asking, where on the graph is the graph going down and where is it going up? So here we can see that our graph is going down in the downwards direction. It's decreasing up until we hit this 4 space here, up until we hit x equals 4. And from 4 onwards, we actually see that it's going in the upwards direction. It's going in the positive upwards direction, which means it's increasing from here. So we are decreasing from negative infinity. Excuse me real quick. We are decreasing from negative infinity to 4. This is dealing with our x values. And we are increasing from 4 to infinity. And this is not including 4 for either increasing or decreasing, because when x is at 4, our slope is in fact 0. So the last thing we want to do is we want to find our intercepts. So we're first going to find our y-intercept. Our y-intercept is when x is equal to 0. So in our function up here, I'm going to insert 0 into each of our x's. So f of 0 is equal to 2 times 0 squared minus 16 times 0 plus 47. And this will be 0, this will be 0. So we find out that this is just 47. So our y-intercept is the point 0, 47. So that's for our y-intercept. Next we want to look for our x-intercepts. So our x-intercepts we can find by, our x-intercepts happen when y is equal to 0. It's the opposite of the y-intercept. So we could set this is equal to 0 and then factor it. But this doesn't look like it'll factor easily, so I'm going to use the quadratic method. So we're setting 0 is equal to 2x squared minus 16x plus 47. This doesn't look like it'll factor easily, so I'm going to put it into the quadratic equation. The quadratic, not equation, the quadratic formula, excuse me. The quadratic formula is x is equal to negative b plus minus the square root of b squared minus 4 times a times c, divided by 2 times a. Plugging in our a, b, and c from 2, negative 16, and 47, our negative b is going to be negative of a negative 16, which gives us positive 16 plus minus. We have b squared, that's negative 16 squared, minus 4 times a, which is 2, times c, which is 47, divided by 2 times a, which is 2. So we have this. This is going to be equal to, let's simplify this a little bit, 16 plus minus. If we plug everything inside of this square root into a calculator, we find out this is equal to the square root of negative 120 divided by 2 times 2, which is 4. And we immediately notice that we have a negative in our square root. If you remember, I'll write it over here, I is equal to the square root of negative 1. Any negative in a square root can be rewritten, including I. Anything that is negative in a square root is an imaginary number. So because we have an imaginary number here, we have a negative square root here, we know that our x-intercepts are imaginary. We could rewrite this using I. And if our x-intercepts are imaginary, that means that we don't actually have x-intercepts. So no x-intercepts. And actually you can see that using our graph up here. We never touch the x-axis at all. It starts here, up here in the air essentially, and it just keeps going upwards, so it will never actually touch our x-axis. And that is the last thing that our worksheet asked us to do, so we are done.